In this video, I talk about unconstrained minimization of functions. The script is called example underscore minunc underscore 1, and we start at line 3 with the usual preamble. We set some defaults. We clear the workspace. I leave figure 1 open. You can see already the contour lines of the function. We are going to demonstrate the numerical minimization or maximization of a function, in this case a function of two variables. Matlab offers two different functions for unconstrained minimization. They are called fminsearch and fminunc. fminsearch implements a gradient-free method, the so-called simplex algorithm, first published by Nelder and Med in the 60s of the last century. It's gradient-free, so it can be used for minimizing functions which are discontinuous or not differentiable, but of course it cannot return a gradient or a Hesse matrix at the end. In contrast, fminunc implements various gradient descent methods, so it needs to compute the gradient of the function and can then return the final gradient and the final Hesse matrix, which can then be used for classification of the stationary point that has been found. I will demonstrate both functions on Himmelblau's function. You see its contour lines on the right in figure 1. If simplex is true, I search with fminsearch and then make a quick run with fminunc just to get the Hesse matrix. If simplex is false, I search just with fminunc. The definition of Himmelblau's function can be found on the web. Let's have a quick look at the web page in the Wikipedia. Here it is. You see the formal definition of the function. It's a polynomial of degree or order 4, and it has 4 local minima and also 1 maximum. One local maximum, which is certainly not a global maximum. Let's first define this function symbolically. We define two symbolic variables and we define the function term, which is now in the symbolic expression f. The minimizers need a function handle of the function to be minimized as its input. So we have to convert this symbolic function to a function handle, which is done in these lines, and this is the resulting function handle. It accepts a matrix with 2 columns. The first column is the first coordinate x1, and the second column is the second coordinate x2. So this is the function handle that we have to pass to the minimizer, which expects this as its first input argument. Now let's produce a contour plot. Let's produce a grid in x1 and x2. This is as usually done by the function mesh grid. Now we have a matrix for the first coordinate with a matrix for the second coordinate. If you want to compute our function on this input, we have first to convert these matrices to column vectors, and this is done in the following way. This is now a column vector containing all elements column-wise of the matrix xx1. So we can do the same for xx2, and now we can compute the function on this matrix. Let's have a look at the dimension of this matrix. This is a two-column matrix which can be fed into the function handle. Now if we compute the function handle, the output, which I call ZZ, is also a column vector, which we now can reshape to the original form of xx1 and xx2 with the function reshape. And now ZZ has the same size as xx1 and xx2. So we can now use this to compute or generate the contour plot. Let's proceed by clearing the figure, setting the color map, defining the contour heights. They are stored in CH. Please note that the contour lines are restricted to the range from the minimum of Z to the maximum of Z over 10. The reason for this is that the function rises very steeply towards the boundary of the rectangle where it's defined. And this is the resulting contour plot. We add a color bar, labels, and a title. You can already see in the contour plot that the function has 4 minima at the 4 corners of this contour plot. It has 1 maximum, not far from the origin, and it has 4 saddle points. Since the function is a polynomial of degree 4, we can find the stationary points by symbolic computation. So let's compute the partial derivatives symbolically, then solve them for 0. This will give the stationary points. We can obtain the Hesse matrix by another round of partial derivatives. We convert the Hesse matrix to a function handle, and we convert the stationary points to numerical values by the function double. If we look at the length of these numerical vectors, we see that we have 9 stationary points. As I said before, 4 minima, 1 maximum, and 4 saddle points. Let's proceed to the classification of these stationary points. So we compute the Hesse matrix, the function handle fh, and compute the eigenvalues by the function eig. If all eigenvalues are positive, we have a minimum. If they're all negative, we have a maximum. If they have different signs, we have a saddle point. Let me now step to line 100. This steps over the graphical representation. So let's go to line 100, and we see in the command window the stationary points, their coordinates, a maximum, 4 minima, and 4 saddle points. In figure 1, we see green circles at the locations of the maxima, of the maximum and the 4 minima, and we see green diamonds at the locations of the 4 saddle points. Now we are ready to call the minimizers fminunc at the moment. I set some options Well, let me set the option display not to none, but to a different value. This will help us to understand what the minimizer actually does. So let me set display to the value iter, which means we get an output at every iteration of the minimizer. I set some colors for the graphical representation, and now we loop over 5 cases, 5 different starting points, and we'll see where the minimizer ends up for each of these starting points. Please note that normally fminsearch and fminunc will find a local minimum, usually, but not necessarily, the local minimum which is closest to the starting point. So if you want to find all 4 minima and the maximum, we have to choose different starting points for each of them. So let's start with the first case. The starting point is at -2 and 2. So the closest minimum is the one in the upper left corner of the contour plot. And we tell the minimizer to look for a minimum by setting the sign, the variable sgn, to 1. So x start is now the point -2 and 2. We also store this point in x final. We skip the function call to fminsearch and proceed immediately to the function call of fminunc. The first argument of fminunc is a function handle which depends on a vector x of 2 coordinates. We multiply the function myFun with 1, which means myFun will be minimized. We give the starting point and the options. Since display has now the value iter, we will get an output for each iteration of the minimizer. Let's have a look. You see in the command window the iteration, the function count. In the second column, you see the function value. In the third column, you see the step size. In the fourth column, and some optimality in the last column. And then it says computing finite difference Hessian using objective functions. So it computes the Hesse matrix by finite difference and the gradient as well. Then we see local minimum found, optimization completed, everything seems to be perfect. Let's have a look at the function value at the end. This is very, very small. The exact value is 0. We can look at the gradient, which should also be very small. Right, here it is. And we see the Hessian, the Hesse matrix, which should be positive definite in this minimum. Yeah, it is. If we look for a maximum, we have to multiply the function we want to maximize by -1, so we minimize the negative. So if we multiply the function by -1 to maximize it, we have then to multiply the function value, the gradient, and the Hessian also by -1 to get it correct. So let's now show the graphical representation. In figure 1, you see the starting point, the blue circle, the endpoint, the blue cross, and a line connecting the two. This line is not exactly the line along the path along which the minimizer proceeds, but in this case it's probably very close because fminunc does gradient descent, so it looks for the steeped descent direction, which in this case is not too far from the line I have drawn connecting the start point and the final point. Now we can do the classification, again using the eigenvalues of the Hessian returned by fminunc, and we prepare a string for the legend, and we print the result. In the command window you now see the start point, the end point, which is a minimum. Let me now proceed directly to the case number 5, the maximum. You can see the 4 minima with their starting points and their end points. Now we set the 5th starting point, which is at 0 and 1. And we set now the sign to -1, so we will minimize the negative function or we will maximize the function itself. Okay, please remember that we now see the negative function values. So after finding the minimum of the negative function or its maximum, we have to multiply the function value, the gradient, and the Hessian by -1. We classify the results. All the eigenvalues are now negative. It's a maximum. And we are finished with our 5 examples. We can now print the legend. I modify its position because it's better outside the axis. Okay, here we are. This concludes this run of this example script. In the legend, we see the 4 minima, the maximum, the exact positions, and the position of the saddle points. Let me now continue with fminsearch. So in this case, we have to set simplex to the value true, and we do more or less the same again. I will now delete most of the breakpoints, and let's stop right here at line 100. The part before that is the same as before, so let's run directly to line 100. Let me also comment the code to the web. Okay. Now we proceed to minimization and maximization with fminsearch. Let me again change the display option to the value iter, so we'll see a printout of the minimizer at each iteration. First starting point, first minimum. Now simplex should be true. Yes, it's a logical one. So we now step into line 125. The calling sequence, the input arguments of fminsearch are the same as the one of fminunc, but of course we don't get a gradient or a Hessian. So let's call fminsearch simplex algorithm. The simplex algorithm has several procedures to find the next point in starting from the starting point, and these procedures are expand, reflect, contract inside or contract outside. Column 3 of this output shows the minimum, the actual minimum of the function. So the first value is 50 at the starting point, and then the function value gets smaller and smaller and smaller until it's below a certain tolerance, and then the optimization is terminated. We now have a final value, x final, the end point of the optimization, and we have the function value, which is very, very small, 5 times 6 times 10 to the minus 16. Now, just for the sake of obtaining the gradient in the Hessian, especially the Hesse matrix, we can append another call to fminunc. This call will do virtually nothing except computing the gradient and the Hesse matrix. So let's do this step, starting from the final point of fminsearch. Only a single iteration is done because the function value is already very small and the gradient is also very small, and we get the Hesse matrix like before. Of course, if you are not interested in either gradient or the Hesse matrix, you can skip this call to fminunc. On the other hand, it's very useful to have an estimate of gradient and Hesse matrix in the stationary point. Okay, the rest is as before. Let's go right to the end. I will now reset the option of display option, so we do not get too much output. You can also just choose the option final. This will give you just the final state of the optimizer. Okay, let's delete this breakpoint and let's go right to the end. And you will see that fminsearch finds exactly the same stationary point as fminunc. This is not surprising because with this starting point, the path to the nearest minimum is obvious. Neither function has any problems finding the local minimum from the given starting points. This concludes this video. I will give a second example of unconstrained minimization in the next video.